Hello students, welcome back. Let us continue with chapter 5, Introduction to Euclid's Geometry. In the previous class, we covered two topics, that was history of geometry and book elements by Euclid. So in today's class, we are going to take a look at the different terms which are definitions, axioms, postulates and theorems. So let us start with definitions. Now why have I written unsystematic? Because we need a foundation why there was a need for definitions. So why there was a need for definitions? Because the mathematicians at Euclid's time, they assumed that geometry is an abstract model of the world that they lived in. So everything was considered as abstract. For example, the points, lines, everything that they saw around, they did not consider that okay, this is that this could be defined. Because for example, if there was an entity like point, if they wanted to define it, they would have to mention the dimension. So define the dimension. To define the dimensions, what are the different dimensions that could exist? So this would be a chain of definitions that would really not end. It would go until infinity, which is why they left these terms undefined. For example, certain assumptions according to the abstract geometrical notion of solid objects were that a solid has shape and size and position. So it has shape, size, position. It can be moved from one place to another. The boundaries of such shapes, the boundaries of such solid objects, they have surfaces. They are called surfaces. Now surfaces have no thickness and are said to separate one part from another. So what we call as boundaries, suppose this is my cube over here. This cube is my solid object, right? Consider a box. So what they are saying is this one has a shape. Of course, this has a shape, it has a particular size and it has a position, because I have placed it at say some 10 units from this from the left edge, right? So it has a position. Now if this suppose this cube was supposed to be real, I could push it, so the position could be the position would change, so it could be moved from one place to another. So solid has shape, size, position, it can be moved from one place to another. Boundaries are called surfaces. So what you call these as boundaries? You can see these lines, these are called boundaries, but they were referred to as surfaces. All these boundaries, they were known as surfaces. Obviously these surfaces, you can see that they have no thickness, because it's just separating two surfaces, right? For example, this is the front surface over here, right? And this is another surface. So they are separating it. Now this boundary, that is the surface, has no thickness. There is absolutely no thickness. Okay, and they are said to separate one space from another. Part of one space. See, this is one part and this is another part. So you can see that this surface, that is the boundary, is separating the two parts, right? So here an important term is part. Why part? Because we don't know what part is, right? So it is an undefined term. Boundaries of surface are curves or straight lines. In this case, you have a straight line as the boundary. But how about curves and straight lines? You know what really curves and straight lines are? Just now we know what curve is. Curve is something like this. Straight line is something like this. But let's say you were from medieval period and you had no idea what is curves or straight lines. So these terms are also undefined. So you can see that according to the abstract geometrical notion of solid objects, certain terms are left undefined. And these lines end in points. You can see that lines are ending in points. Here also the lines are ending in points. But what are points? We don't know points. So in every definition, what is happening is that we are losing one dimension. So what Euclid did is, just invert. So what Euclid did is, he defined these terms such as part, curve, straight line, points. Okay, so there were 23 such definitions. So these were statements. Statements, why? Because it defines certain terms. Some of these are here, but they are not in order and these are all listed into the book 13 Elements. So the first one is, a point is that which has no part. So a point is something that has no part. A line is a breathless length. So a line, just take for example your number line that we did in chapter 1. What did we say? Line, why we draw these arrows? Because the line extends indefinitely in both directions. So here a line is a breathless length. It has no breadth. You can see that it has no breadth. See, this is just one single line. There is no breadth, no? Right? And it is extending indefinitely in both the directions. So it has no defined length, no limited length. Then the ends of the lines are points. So if let's say we have, this is actually segment. So segment, it ends in points, right? The end point, and we also refer to these as endpoints. Then a straight line is a line which lies evenly with all the points on it, which lies evenly with its points. So this is a straight line, okay. Obviously this is made up of several points. There are so many points. See, these are the points. I'll do it with a different colored chalk so that you can. So this is my line. These could be the points, right? So with all the points on it, the line is lying evenly. That is, the line is lying evenly on all the points that lie on it. So this is the definition of this sentence, the statement. Then and then we have the surface is that which has length and breadth only. For example, consider this board. You have a length and you have a breadth, right? So this is my length, the upside and the downside, this is a length, or you can just take this duster for example. You have a length and you have a breadth. Keep it in any direction. You will always have a length and breadth. So, and the edges of the surfaces are lines. Again, take this duster for example. You have the edges as lines. These are plane lines, right? And plane surface is a surface which lies evenly with the lines on it. So I'll take this duster again for example. Now this is a surface. Just consider this part. Don't consider it as a three-dimensional object. Just consider what I'm showing. Just see what I'm showing you over here. So if I draw lines over here, there can be so many lines. There could be lines like this in a vertical direction, or they can be horizontal lines. So on the surface all the lines are lying evenly. So you can say the surface lies evenly with all the lines drawn on it. So these were the definitions. Now based on these definitions, Euclid defined certain properties, and these properties are further divided into postulates and axioms. So what are postulates and axioms? Axioms are universal truth. Properties that are universally true. So axioms are not just limited to geometry but universally. It could be algebra, it could be something in your daily life. You will see it when I will go through each of these axioms and give you examples. And postulates are properties that are specific only to geometry. So specific to geometry. So in today's class we are going to take a look at axioms. Postulates will be taking a look in the next class. So these are certain axioms that have been provided in your textbooks, but this is not in the order provided in the book, the actual book 13 elements. So some of these that we would learn are these 7 points that I have mentioned, which are nothing but properties. So axioms, as I mentioned, these are universally true and not just applicable to geometry. They could be applicable to algebra also in your real life. So I'm just erasing this section because I'll be needing this side of the board for explaining you the different axioms. This is a very theoretical chapter, so I hope you are taking down points that I'm listing on the board. And you might get to name the axioms, or write all the axioms in your exams. So just make a note while I'm teaching you. So let's take a look at the first axiom. Things which are equal to the same thing are equal to one another. So before I go into the explanation, we'll see these axioms, how they are applicable in geometry as well as in algebra, also in real life. So I'll give you 2 or 3 examples, or just one example wherever applicable. So the first one, things which are equal to the same thing are equal to one another. So what does this axiom mean? Let's say I have a line AB which is equal to line BC. So AB is equal to BC. If suppose this is 5 centimeters, this is also 5 centimeters, correct? If I take a third line, say PQ, and I say that PQ is equal to AB or AB is equal to PQ. So this is also 5 centimeters. Does this mean that BC and PQ also equal? Yes, BC and PQ are equal. Why? Because they all are 5 centimeters. So even if it's given explicitly that AB is equal to BC and AB is equal to PQ, you can say that AB is equal to BC, which is equal to PQ, which is equal to 5 centimeters, right? So this was an example in geometry. Now let's take a look at an example in algebra. If I say that x is equal to y, okay, and I say y is equal to z, will x be equal to z? Yes, it will be. Now let's say I have taken my value of x as 3, the value of y will also be 3. Again y is equal to 3, so z is also equal to 3. So therefore x is equal to z, yes, because x is 3 and z is 3. So this is what the first axiom means. Now the second axiom. If equals are added to equals, the wholes are equal. That means if I have two numbers, let's say 5 and 5. Okay, so 5 is equal to 5. Now if I add a number 3 to both sides, so 5 is equal to 5. If I add 3 to both the sides, will my resultant output be equal? Let's check. 5 plus 3 is going to give me 8 and 5 plus 3 is going to give me 8. So obviously the result is equal. This is what this axiom means. If equals are added to equals, the wholes are equals. That means you have 3 added to 5 and 5. So 3 added to 5 on the left hand side and 3 added to 5 on the right hand side. So the output that we got is equal. Similarly, now the third axiom, what does it say? That if equals are subtracted from equals, remainders are equal. So enough of algebra and geometry. Let's take a real life example. Let's say I have one pizza, another pizza. They both are 6-inch pizzas, okay? And if I eat up half of it, half of the first pizza, and let's say you eat up half of this pizza. So how much am I left with? I am left with half the pizza, and you are also left with half the pizza. They both are 6-inch pizzas. So how much is left? 6 divided by 2 is left. Here also 6 divided by 2 is left. That means 3. So the remainder that we got is equal, right? So this was just an example. These are not the actual numbers. So you're left with half pizza, I'm left with half pizza. So that is, if it was a 6-inch pizza, you're left with some 3 inches, okay? Things which coincide with one another are equal to each other. So coincide, what this coincide means, when any two entities meet at a certain point, okay? So let's say I have a circle and I have another circle, both having radius 3 centimeters. This also has 3 centimeters and this also has 3 centimeters. So obviously you can say that these are equal. Now if I move this circle on top of this circle, what will I have? I will have an overlapping circle. boundaries of this circle will lie on the boundaries of this circle. So what I have is nothing but there's one circle and top of this there is another circle. So for example, I take, let's say, 2 chalks, these are equal in length, okay. Now if I coincide, so my example was something like this. I have 2 chalks, so I take this one chalk and the other chalk, now I place it on top of the other. So they are coinciding with each other, right? Now since they are coinciding with each other, they are equal, which is what this statement means. Things which coincide with one another are equal to one another. So it's coinciding. If I am placing this chalk in front of the other chalk, you are not able to see the chalk that is behind, right? See, you won't be able to see the chalk that is behind. So that means these 2 chalks are equal. The whole is greater than a part. This is very self-explanatory. Again, let's take a pizza's example. This is one whole pizza. If I remove this much from this, what am I left with? Two parts. Right? I remove 1/4 of the pizza. They are not equal, but I'm just consider that these two are equal. I have cut this section 1/4 of a pizza from this entire pizza. So obviously this is smaller than this entire pizza, and also this section, the second. So I have 2 parts, 1 part and 2 part, and this is the entire part. So the part 1 is smaller than the entire pizza, even part 2 is smaller than the entire pizza. So this is what a axiom means. The whole is always greater than a part. The whole is always greater than a part. Okay. So now the 6th one. Things which are double of the same things are equal to one another. So let's take an area of an area for example. Let's say I have a square of 5 centimeters and I have one box that has double area. I'll call this box A, I'll call this box B. So I'll say the area of B is double the area of A. So this is going to be how much? 10 centimeter squares, correct? And I'll say there's another box C that is double the area of A. So this is again going to be 10 centimeter squares, correct? So can I say that B is equal to C? Yes, because we can see that both are 10 centimeter square. So this is what axiom 6 means, things which are double of the same things. So things which are double of the same thing, they are equal to one another. So B is equal to C over here. Box B, area of box B is equal to the area of box C. Now things which are half of the same things are equal to one another. So again I'm going to take the pizza's example because we all love pizzas. I love pizza. So I have this one whole pizza. It looks more like an egg. Let me just make it more round. Okay. Now things which are half of the same things are equal to one another. So I have divided this circle, this pizza into 2 halves. So this is part 1 and this is part 2. This is half of the pizza and this section is half of the pizza. Or if you want, we can just do it this way. This is exactly half and this is exactly half. Obviously they are equal, right? So just to make it look more like a pizza. So I have 3 pieces here and I have 3 pieces here. So these 3 pieces and these 3 pieces make an entire pizza of 6 pieces. So things which are half of the same things are equal to one another. So these were the axioms. Let's take a look at the postulates in the next class. Thank you.
Hope this video increased your knowledge. For more such videos and a completely free educational content, log on to www.epathshala.org or visit our ePathshala YouTube channel. We have each and every question solved for maths, physics, chemistry and biology. So subscribe our channel, share with your friends, like our Facebook page and follow our Twitter handle for regular updates and important educational tips, and also win ePathshala goodies. So what are you waiting for? Subscribe this channel and enjoy the freedom of education.